Hi, everybody. Chuck White here with my friend and collaborator, Rich Kingsford, and we are from chemvantage.org. Chemvantage offers affordable, high-quality LTI homework, quiz, and assignment apps for general chemistry. Today, we're talking about using analogies and visual models for students who just don't get it. Um, Rich, when a student says, I just don't get it, what cognitive process is usually failing? And how does this relate to the current mental model?
I think a common one is focus. Are they able to focus on the problem? I think another one is understanding. I think a lot of students will read the question and not, even if they don't understand one word, it can just stop everything in its tracks. And maybe there's a conceptual model. Maybe there's I don't know what the name of it is, but there's a type of logic where you put multiple parts together and conclude. There's logic that puts lots of small things together to form a conclusion, and then there's the reverse logic where you're taking something and breaking it down into separate parts. So I think that it might be one of several different cognitive processes. I think the teacher's job becomes to diagnose which one is, where's the problem here? Where's the confusion here? What do you think?
Yeah, I think that's right, but um, I think also students often need some scaffolding, something to sort of hang a new idea on. If they lack the ability to relate a new idea to something that they already understand, then it's much more difficult to process it and come up with a deep understanding. But if they already have a scaffold, something that they understand, and they can just extend that to a new idea, then I think it's much easier for students to bring on some new knowledge.
Yeah. And I think it's reassuring too emotionally where, oh, I'm familiar with that thing. So let me fall back to that and then build on it. Love that.
Yeah, as long as it's a good model. If it's a lousy model, then it doesn't work.
Yeah, then it'll be extra hard to teach it. Agreed.
Yeah. So, what are the limitations of purely algebraic or abstract instruction for the bottom 10% of learners? And why do these methods often fail to trigger true conceptual change?
I think the limitation is it's a poor, highly abstract things are poor simulations. It's the more abstract something is, think of a Picasso painting, the further it is from reality. And I think that's the most severe limitation. It can be, very useful to abstract something, so long as it's not a too big of a stretch for the student. We abstract things all the time. It's only practical to abstract things, and oftentimes it's impractical to make a 100% realistic model or a realistic simulation or a realistic representation. Pixel for pixel perfect photo might be really hard. Maybe it's more practical to use a crayon sketch every once in a while.
Mhm.
So so long as you're not causing this huge gap, you're not introducing a bunch of confusion with to in the mind of the learner. I think
Yeah,
that's where it fails.
I think sometimes the way that math is taught really defeats the purpose of learning math as an abstract model for the way the world works, because students too often just learn math as a set of procedural steps. It's a recipe for doing a certain operation, whether it's a simple multiplication or long division or um, steps to isolate a variable. If they're just following rules to to get some physical result or some mathematical result, then it's really much harder for them to use mathematics as a model for the world. But if they are able to conceptualize that, if I double this particular quantity, then this other thing is going to be cut in half, or it'll also be doubled, or maybe quadrupled or quintupled, then then that serves as a model for how the world works. So if the thinking is operational, if it's just rule following, then it's going to be really difficult for students to use math to understand a new domain.
Yeah, I completely agree. I'm thinking of word problems, story problems. And when I was a young student, those word problems were always at the very, very end of the chapter in my math or algebra, calculus, whatever textbook. And we never got to them. So the teacher would show the procedures, the X and Y and the single letter variables. And I got through that okay. But then when I would get to the story problem, I get really nervous and think my first thought was, we didn't cover this. And I think that is such a shame. I think word problems and story problems are so underutilized,
Well,
but
I think
maybe
it,
someday we'll fix it.
they train students or everybody to solve real problems in the real world
Yeah.
because those come from stories.
Yeah. When you have the job that requires you to solve the problems. Yeah. I think those are wonderful story problems.
So
In
we've
fact, I
talked,
have to share one real quick.
yeah, sure.
My 12-year-old is selling cotton candy this summer for the first time. And you can imagine my excitement. I love her ambition to do that. Of course, she didn't have enough money to buy a decent cotton candy machine. So I lent her the money. And as part of I didn't gift her the cotton candy machine. I lent her the money for one. And as one of the rules, one of the contingencies for me doing this was she would have to show me on a spreadsheet uh, the her break even point. When she would pay back the loan and the
Mhm.
financials on the spreadsheet. Wonderful story problem. And I can't say she didn't roll her eyes about 100 times, but I I hope she learned something about fi true algebra, and really doing some real not abstract simulations, but real world story problems.
She's 12 years old.
Yeah.
You are a tough parent. You are a tough parent. Wow.
It was fun.
Goodness.
It was fun to see her struggle through it.
So
Of
we've talked
course, we
about,
made the spreadsheet pink
yeah,
and
okay.
multicolored. We didn't
Yeah,
have a black
yeah,
and white spreadsheet. That
okay.
if I did that, then I would be a tough parent.
Okay. We've talked about the advantages of using analogies in STEM instruction, but what are the biggest risks of using a poor or incomplete analogy? And how can a teacher ensure that they don't introduce new misconceptions?
I think the biggest risk is introducing that confusion, or you exacerbate the confusion. If Yeah, there's so many different things to study and so many different things to learn, but in any of them, if if I'm trying to make a point with my story, with my analogy, but it's poorly delivered, maybe I go too fast, maybe I go too slow, maybe I'm a poor storyteller. It's it- you have to maybe I don't tell enough jokes with my analogy. And there's a little bit of entertainment involved with preserving attention. Then I think, yeah, you can make things worse with the analogy. I mean, I think another one is linear. There's these a lot of times the concepts will build. You'll start with the very basics that provides the foundation. You master concept A before you move on to concept B. And if even one student fails, struggles to master that letter A, and you just move on, I think that risk of introducing more confusion comes into play. What do
Yeah,
you think?
I think that it is important to stress the limitations of analogies to really figure out where the boundaries are. And maybe it helps to have multiple analogies for each concept because um, no one analogy is going to map completely onto a concept that you're trying to teach. But if you use multiple analogies, then students will more easily see which parts of the analogy really do map onto what you're trying to teach.
Yeah. Yeah, I guess I prefer as close to one-to-one mapping as possible. I want to simulate the real world as best I can. And some of these analogies, they just get, if they're such a stretch, if they're so abstract, I get nervous.
One of the problems in chemistry is that um, the analogies that we use tend to be macroscopic things in our everyday world, but the things that we're trying to teach are microscopic things on a scale of molecules, where things like friction and kinetic energy don't have exactly the same interpretation as we do for macroscopic things in the world. So I think you have to be a little bit careful about the way that you use analogies.
Yeah, that's a good point. In fact, you and I, a while back, we were thinking about 3D models. Nowadays you can 3D model just about anything with a single AI prompt, and
Hmm.
you can make videos with AI prompts too. And
Hmm.
I once tried to make was it an atom? I think I was trying to simulate an atom, and I showed you a reference picture. Do you remember what you said about it?
I don't remember.
Or maybe it was a video, but the electrons were spinning in a nice
Oh,
clean circle around it's a nucleus, right?
yes.
And and do you remember now what your
I don't
criticism
remember
about it?
what I
You
said,
you
but
you said
it's the
they're
same
not
mistake that
vibrating. It's not so clean. The real
yeah,
world's not so clean, but I think the electrons vibrate. Or you said a more accurate one would be if they jittered or something.
something like that. Yeah, they have a statistical interpretation rather than a classical interpretation like you would in a macroscopic object. Yeah.
Yeah. So I'm thinking those criticisms with the simulations are valuable. You might have an analogy and you might say, here's a 3D model of an atom, but there are three things about it that really bug me. And you could list the three things,
Yeah.
especially with AI you and I have tried to generate a couple images, chemistry images, and
Hmm.
each one of them had at least a handful of inaccuracies. And I,
Yeah.
I like to think there's lessons in there. If we took that image and say, okay, this is bad in at least three ways,
Hmm.
then I
Hmm.
think you can use the inaccuracies in whatever simulation, whatever model, and you can use that to teach the students, or maybe further confuse them.
Interesting to use the flaws in an analogy to teach what the truth is. That's
Right, right.
interesting.
That's the goal anyway.
Yeah.
I have limited experience in trying it.
Well, moving on, what are the core steps a teacher should follow to effectively introduce and deploy an analogy to teach a new concept?
I don't know if I like core steps. I think core steps can get boring, and I like to try and keep the students on their toes. But there might be some principles here. There's there's the foundation. I think I prefer a story here. And to the word analogy. And every story has to start with something familiar to the students. So you begin your story with some sort of introduction. And I think it's even okay to state the goal, say the goal of my story here is to drive home, whatever concept. We're comparing current flow to water flow or whatever concept you're trying to teach. And then I think you tell the fun part of the story. Whatever, if it's an analogy, fine. If it's not an analogy, that's fine too. Then I think you do the conclusions. Sometimes there's a nice clean map, but there's some sort of leap between the simulation, the analogy, the thing that's on the one side, and then reality on the other side, the true concept you're trying to teach on the other side. So you show them, so maybe you can help them visualize the side by side comparison, whatever. Then I think there's limitations too. And I think it's okay to highlight those limitations and say the phrase, this isn't a perfect analogy, or this isn't completely parallel because of blank. What do you think?
Mhm. Yeah, I think that's right. It is important to point out the limits, um, but I think you can also go one step further and ask the students to predict an outcome in the target domain using the source model. So if they understand um, the the analogy and they understand the target concept that you're trying to teach, and you've done the mapping properly, then they ought to be able to make some simple predictions in the target scenario to make sure that they really understand what you're trying to teach.
I like that.
How can we move beyond simply showing a visual model to using it as a tool for sense making, especially by highlighting the isomorphism between the model and the real concept?
Hmm. Isomorphism is that one-to-one correspondence between the two systems. So
Mhm.
the physical model and the abstract model, that
Yeah, the
relationship
mapping.
there.
Yep.
Yeah. Um, Tough one. I thought this is a very tough one. I think it's making the answer is making the students part of the experience, not just, don't just present a slide deck and step through the slide deck or just read the thing. Get your fingers dirty. The maybe instead of showing an existing model, you make a model, or you invite every student to use AI to to make a model, a 2D model or a 3D model or a piece of code. You know, a lot of people don't realize that a layperson can now code an app. They can ask AI to code a simulation in in about 5 seconds. It's once you see it for the first time, it'll blow your mind, and it might scare you a little bit with how powerful it is. I've seen a lot of people. These are even my superiors, my 40-year-old, a 40-year-old, a 50-year-old, a 60-year-old person who's never coded a single thing in their life, building an animated 3D simulation of something.
Mhm.
It's in one single sentence. It's crazy. But anyway, back to you get this, you help the student get their fingers dirty. And as they build the model, then I think the probability that that light bulb will turn on uh, gets a lot stronger. It's not just building it too. There's testing it. There's predicting what's going to happen. There's all sorts of little tiny games you can play with any STEM subject. And I think playing those games and you know, don't just jump to the conclusion. Don't just jump to the assertion, the piece of truth. Have fun, make it a journey, make it a little game, and after a few minutes of struggling, of some work or play, then you get to the solution. I think that's a common mistake with teachers. It's they know the answer. I'm the expert. I know the answers. I'm just gonna throw the answer at you.
Well, I think that you're right that having students make predictions really helps them to understand what's inside the black box.
Yeah.
And that's really what we're after is to have them understand how the model works, what's inside the black box. If I turn this knob to double this one input, how does that affect the output? Um, and if they can make those predictions, then I think that's an indication that some real understanding is going on.
I like that. Or maybe if something doesn't work, there that's what the power of testing comes in. I thinking oftentimes when we're teaching, we give a really clean story and nothing goes wrong. We just we just show the concept and say, "Look at this. It works every time." Okay, get to your homework now. But what if we showed the failing cases more often? In
Mhm,
programming, there's bugs. A lot
mhm,
of programming is dealing with fixing bugs.
mhm.
And maybe we could show the bug. We start with the bug and we say, something's wrong here. There's something wrong with our model. There's something wrong with our simulation. What's the problem? And you see if the students can debug it or if they can diagnose and discover the problem. And then
Yeah.
later you get to the clean model.
Interesting idea. So let's talk about dual coding theory. This is a theory that suggests that information is better recalled when it's presented both visually and verbally, but not identically at the same time. So, how do you think dual coding theory supports the use of visual models and analogies? And what does this mean for lesson design in a lecture setting?
I think these two, they're using different parts of the brain. And I've heard that it to truly teach something or to tell a story effectively and make it entertaining, you want to tap into the senses. The more senses, the better. Taste, smell, ears, hearing and visual. And I think that maybe there's some parallels here with that. Personally, I'm a big believer in breakout groups where the students discuss things. Every single one of my lessons, I would try very hard to keep my lectures under 30 seconds. And then I just do a breakout group very, very quickly. And I struggled. That was kind of a goal, and sometimes I often didn't hit that goal. But I want the students talking in groups of two or three, and I want each student to say something. I'm a big believer that when I'm talking, it's using different muscles in my brain and it's triggering different ideas and helping me make sense of something that I'm not very familiar with. And
Mhm.
maybe I'll say a lie, maybe I'll say an error. But I think there's worse things. There's there's worse things than saying some BS. And I think I have to make a handful of mistakes before I can master something. It's mastery is messy. I'm thinking it's not this clean process where I'm mastering something. I'm gonna I'm gonna fumble and stall and say something that's not perfect.
Yeah. I can't tell you how many presentations I have sat through where somebody had a PowerPoint slide up and then just read the words that were on the PowerPoint slide. And this really causes a lot of cognitive interference because your eyes are usually not going across the words at exactly the same time as your ears are hearing the speaker read the words.
Yeah.
And uh, so it's not only redundant, it's just it's has a negative outcome.
Yeah,
But
agreed.
I remember watching Steve Jobs give presentations when he was alive. And what he would often do is he would have a picture on the presentation and maybe a few words, like 3 or 4 words at the bottom. And that sort of framed a conversation. But then he
Yeah.
would talk about it. So in your mind, you were looking at the picture, you could look at 3 or 4 words and understand the context of what was going to be said, and then focus on Steve's description of whatever it was he was trying to say. And I think that having your visual input and your auditory input um, be different but complementary really helped to drive home the point. And I always tried to structure my own presentations in a similar way. I wasn't nearly as successful as he was, but I think in terms of analogy, what you can have is a clear visual model and then verbally explain the mechanism. And you can allow the verbal stream to direct attention to specific visual features in real time without actually duplicating the verbal and the visual at the same time.
Yeah. I like that. And I'm thinking it's easier said than done. It's really easy to say all the theory, but
Yeah,
I'm thinking a good feedback mechanism is engagement with the students. You can kind of feel in the air in the room if students are genuinely interested or if they're just trying to suffer through the thing.
yeah. So we're almost out of time, but I wanted to ask one more question. And this is kind of a take-home lesson, but what is the single most powerful technique a teacher can use to help a student to discard a deeply entrenched but incorrect mental model? Um, like the belief that heat is a substance. How do you do that?
Good question. I'm thinking a project, an experiment, a test is my answer.
Mhm.
Something where, I- if I'm inviting the students to discover something for themselves, I'm not telling them the answer. I'm not telling them maybe not even the hypothesis, but I just want to throw them into something that is cool and that I think will spark their interest, and then a little bit of structure. There has to be some sort of goal, and we live in the real world where there's time constraints. So I want them to achieve an objective. My favorite is 20 minutes. We'll break out for 20 minutes and then we'll come back, we'll reconvene and see what we learned. Um, but it's okay to make a mess, and it's a little scary to imagine what they might do, but man, I did this for 11 years, and I was very often surprised at what the students would come up with. I know a lot of them would just surprise me and come up with a deep insight and make me go, I didn't think of it that way.
But how do
I,
you disabuse them of an incorrect model?
Through testing, yeah, if it passes the test, then that's a pretty good indication that it's okay. Now, there's also false negatives and false positives in your tests, and it might be a
Mhm.
bad test. So so it's important to test your tests. And I think that's another good lesson to include is okay, we built this thing but our tests are flawed. Now we need to build tests for our tests.
Mm. So you could ask them to make a prediction with their model um, that that it produces a false outcome,
Yeah,
or at least a an implausible outcome.
I like that.
So
That's exactly what I mean. Sorry, I'm when I say test, I'm talking about a test like you would in programming, where you have an assertion, you're expecting something,
Mhm.
and maybe the thing does it as you expected, or maybe it doesn't. And yeah, it's the prediction of, okay, here's the outcome I expect, and we might get it, we might not, but either way, we need to understand what's happening.
Yep.
Is that your answer? The prediction, a predicted outcome is the single most powerful technique?
I think so. It's kind of hard to do in a lecture setting, and it's risky because you're never quite sure what parts of a prediction are going to get the student is going to get right with an incorrect model and which are going to get wrong. Um, but I think if you have the time and um, capacity to really dig into uh, an incorrect model, having a student fail to make a prediction with their deeply held belief is a very powerful way of getting them to change their minds.
Ooh, I like that. Powerful techniques.
Yeah. So this has been fun. Thanks for joining us. Uh, Rich and I are from chemvantage.org, and ChemVantage offers affordable, high quality LTI homework, quiz, and assignment apps for general chemistry. It's been fun, Rich. Thanks for joining me.
Thanks, Chuck. Bye bye.
Bye.